All right. Welcome, everybody. This is our last meeting of this semester, and I'm very excited to have Daniel Durstewitz join us. I hope I pronounced that correctly. Daniel, could you please tell us a little bit about your interests, your research trajectory, how your interest evolved, and um, what got you interested in the question that you're going to tell us about, like continual learning from a neuroscience perspective?
Yeah. So first of all, thanks a lot for giving me the opportunity here to present some of the ideas and thoughts we have been thinking about. So maybe the best way to start is I actually introduce our group, our lab, and
Hmm.
then I'll go into a bit more specifics about your question.
Hmm.
So we are the Department of Theoretical Neuroscience at the Central Institute of Mental Health, as well as at the Center for Scientific Computing at Heidelberg University and the Faculty of Physics. So we are already a quite interdisciplinary group. And we have a couple of fundamental interests. So our core topic or theme at the moment, I would say, is scientific machine learning, or what has come to be known under this term, where we develop methodology specifically for multimodal, multivariate time series from a dynamic systems perspective. So the dynamic systems perspective is something that is very important to all of our work, and which will also be apparent from my perspective on this topic of continual learning.
Hmm.
So a second area in our group is essentially data analysis using our methodologies in neuroscience and also in more generally in biomedical applications. And continual learning or neuro AI, as some would say, I would say is a bit more of a recent interest. So we have a long track record in both computational neuroscience. So actually, I've been in California for a couple of years myself at the Salk Institute a long time ago with Jerry Sinofsky. And even before that, I always was interested in this mixture of AI and neuroscience. I originally studied both computer science and psychology because I was interested in both artificial intelligence and human intelligence, you might say. And even at the time, I would say, for instance, my master thesis I wrote on neural networks and how they could be applied to human subjects. So I have let's say, a long-standing interest in these areas. Um, and my talk today, shall I continue now with my talk, or are there any other questions you are interested in?
I think it would be nice if you could maybe stay on this, broader, big picture at the that level a little bit more, because I wanted to ask you, for example, you're highlighting dynamical systems thinking. I guess we're gonna get into the technical details of that in the talk, why it's interesting to you and why do you think it's useful for both neuroscience and machine learning. But do you think we could spend a little bit of time just talking about the high level, big picture motivation? Why is that your favorite way of thinking about these things?
You mean the dynamic systems perspective? Why it's my this is my yeah. So
Hmm.
there are several reasons for that. So first of all, dynamic system theory is a very fundamental theory. So it's a
Hmm.
mathematical theory you could almost throw
Hmm.
at anything evolving in time, and the
Hmm.
brain specifically.
Hmm.
And I think many of you know that dynamic system theory really has a long track record in computational neuroscience. So
Hmm.
dating back at least to the work of John Hopfield, I would say, so this is an obvious
Hmm.
example of where dynamic systems theory has been very successful in its application to neuroscience. But the brain neurons are dynamic systems. So they are described, we
Hmm.
describe them usually by sets of differential equations. Dynamic system theory is a theory that deals with the long-term behavior of such
Hmm.
systems.
Hmm.
It has a lot of interesting implications and connotations. Yeah, so our real
Hmm.
world, I would say, in most of its aspects, is also a dynamic system. Yeah, giant
Hmm. Hmm.
dynamic systems. Yeah, certainly the physical
Hmm.
world, but also
Hmm.
most of the biological world or social world.
Hmm.
So, in my view, dynamic systems are really fundamental for our understanding of both nature and the brain.
Hmm.
And also, they make the connection between the two. Um,
Hmm.
for instance, one interesting aspect about dynamic systems theory is it's Turing complete. Yeah? So any
Hmm.
computational process you
Hmm.
can realize or reformulate as a dynamic system.
Hmm. Hmm. Perfect. Yeah. I guess another personal curiosity maybe that I would add here is that, yeah, if you think about the learning dynamics of a neural network, the optimization process, that is also a dynamical system. So it truly is, maybe we can call it a theory that can be applied to everything, including neural networks. So okay, I guess with that introduction, maybe yeah, let's jump into the actual presentation. Thanks.
Okay, thank you very much. Yeah, I completely agree. Yeah, so even
Hmm.
training algorithms and in machine learning are usually dynamic systems.
Hmm.
Okay, so learning in non-stationary environments, so that makes a perfect transition to my actual talk topic. As I said in the beginning, most of what we do is really connected to dynamic system theory. So this is a bit of a more recent topic we dive into. The observation from my point of view is that current AI system are really fundamentally different from the brain in the sense of dynamic systems. So, as I already mentioned, natural environments are dynamically evolving. They are fundamentally dynamic systems, both the physical and the biological or social world, evolving on many different timescales. And I think the brain needs mechanisms to extract that. Yeah. So, in a sense, you might want to say it needs to resonate with all these dynamical properties evolving from milliseconds to years or even decades, yeah, throughout a lifetime. Maybe that's sort of an interesting anecdote, but I mentioned in the beginning, I started out with studying computer science and psychology, and one psychology class dealing with perception discussed the work of James Gibson. I don't know whether you know him, but he is sort of in opposition to the constructive view or constructivist view of the brain or mind. He proposed that sort of the brain naturally extracts a lot of properties. Yeah, and at the time, I must admit that didn't really make sense to me before I learned about dynamic system theory. Yeah, because from that point of view, you might really say, okay, in a sense, the brain needs to somehow resonate. Or reflect these dynamical properties. And that might be a sort of a formal meaning that you could give to these types of theories. So I think that's most obvious in music, yeah. But also in phenomena like if you are in a theater and you are starting to clap hands and you start to synchronize with other people, for instance. Okay, so I think this is
Actually,
really
can I jump in?
sure.
I'm very curious. So since you brought this up, that's a very interesting point to explore a little bit. The contrast between constructive and Gibsonian affordance kind of view. Um, I do you think that they're fundamentally incompatible? Because to me, it seems like if you take, let's say, Helmholtz's perception as inference, and then the Gibson's idea that perception is about like extracting affordances, if you frame extracting those affordances as another inference on a distribution of possible actions you can take, it seems like you can actually unify these views. They are not fundamentally incompatible. So I was
Yeah.
curious to hear your thoughts.
Yeah, absolutely. I mean, it's to
Yeah.
me, it's kind of obvious that the brain constructs a lot of things. Yeah. So, I mean,
Okay.
we
Hmm.
make up reality in a lot of
Hmm.
different ways. Yeah.
Hmm. Hmm.
To an extent that I sometimes find frightening, but that's a different story, I guess. No, both have some truth to it, I guess. Yeah.
Hmm. Hmm.
Yeah. So I completely
Hmm.
agree with you on that.
Perfect.
Um, but there's another, I think, important aspects about environments. So they are not just dynamic systems, but they are continuously changing. Yeah, so they are non-stationary in the statistical sense, or non-autonomous in the dynamic system sense. Yeah, so that means that if you think of it of a dynamic systems, it means that the vector field describing the system is not constant. It's constantly changing in time. Yeah, and I think that that is strongly related to this whole idea of out of domain generalization, um, and that is something that I find extremely exciting, and where I think there are really large gains to be made. Yeah, so I think it's almost like a holy grail of a lot of AI and also brain research. And that's sort of something where I will basically give you my thoughts and ideas on. I won't present actually that many results, but I basically want to discuss with you some of the ideas we had. But coming back to this here, let me stress that in my view, AI has almost nothing of that. Yeah? So transformers are not even dynamic systems. Yeah? So and they cannot easily extract or learn dynamic systems. Yeah? So I think from my point of view, we really need to switch or change the models we use in AI fundamentally if we want to approximate capabilities that the human brain or mind has.
Can you elaborate why do you think that transformers are not dynamical systems? First of all, I thought that if you can express the time evolution of something using differential equations, then maybe like in a Euler time discretized kind of way, you can roughly think of it as dynamical system, but maybe that's not a precise definition. So can you help us understand why you don't consider transformers as dynamical systems?
Yeah, so I mean, you might want to use them in an autoregressive or recursive way.
Hmm.
Yeah, and then in a
Hmm.
sense, they are dynamic systems, and also dynamic system theory has been applied to understanding across layers
Hmm.
processes and transformers. And so this is
Hmm.
true. What I meant by
Hmm.
that is that in the first place, um, they are designed to get rid of a recursive description, right? So the
Hmm.
major one of the major motivations in the design
Hmm.
of transformers was to solve this computational bottleneck that recurrent neural networks have, and
Hmm. Hmm.
by doing so, they basically got rid of this recursive description
Hmm.
that you
Hmm.
need for a dynamic system,
Hmm. Hmm.
and also they sort of kicked out time. Yeah, so I mean
Hmm. Hmm.
through this attention mechanism. Yeah, so
Hmm.
and that's the reason why they had to introduce time through the
Hmm.
back door by
Hmm.
this encoding mechanisms. Yeah,
Hmm.
but
Hmm.
it
Hmm.
by doing so you lose the true dynamics of any underlying system. Yeah, so I
Hmm.
think
Hmm.
that's a fundamental point in my view. Yeah.
Okay, I think yeah, the standard traditional or maybe like the standard way of thinking about transformers definitely does not look like a dynamical system, but I think there are recent reinterpretations, I guess, I don't know what to call it. There are some papers coming out, and in fact, we had a guest earlier back in February. He presented his work called nested learning, and in there, they show that you can derive the transformer architecture from some associated memory objective plus optimizing that objective that derives the linear attention, not the transformer. But anyway, I think there are ways that you can actually reinterpret these architectures also as just a dynamic recursive process. So you might
Mhm.
be interested in this. Yeah.
Yeah, yeah, yeah. No, I mean, at at the point where you are using them in an autoregressive way. Yeah, so
Yeah.
then you
Yeah.
are essentially using them in a recursive way. I mean, recursion
Hmm.
is fundamental to dynamic
Hmm.
systems. Yeah, so it's
Hmm. Hmm.
defining for dynamic systems. Yeah, so you need
Hmm.
something like that in there.
Hmm.
But you can also view processes across multiple stacked layers as a recursion, and
Hmm. Hmm.
or iteration. Yeah. So I'm aware that there are many dynamic systems view on transformers. Yeah, but
Hmm.
I
Hmm.
still
Yeah.
would argue
Hmm.
that they are not suited as a, or not so well suited as recurrent neural
Hmm.
network as
Hmm.
a
Hmm.
or as neural ODEs.
Hmm.
Um,
Hmm.
yeah, for learning dynamic systems.
Okay, that makes sense. Yeah, thanks.
Okay, what are the issues in non-stationary environments or learning in non-stationary environments? The first and most obvious and most well-known one is catastrophic forgetting. Yeah, so that has been around for a couple of decades. Actually, I should mention this is an AI-generated figure, but I was actually quite pleased with the outcome. It's based on an older paper by McCloskey and Cohen, and by Kirkpatrick, PNAS paper on elastic weight consolidation that some of you might know. Catastrophic forgetting really means that if you learn different tasks in a sequence, then usually your performance drops dramatically on tasks that you have seen previously, unless you do something. And that is rooted basically in the fact that there's some optimal parameter regime for some task A, and as you keep on training your device, you will basically move the state out of that optimal parameter regime. Yeah? So you need to do something about that to counteract catastrophic forgetting. And it's also related to this old stability plasticity dilemma. I'm actually not sure who coined the term, but it might have been Stephen Grossberg. Yeah. So this is one issue. But another issue that I actually find almost more interesting is how brains can quickly adapt to novel contexts or environments with minimal data. And I think that is a point that is really quite different from how machine learning algorithms are generally trained. Yeah, so um, they, I mean, gradient descent usually needs millions of repetitions. Yeah? And if you use, let's say, straightforward, out of the box reinforcement learning, it's the same thing. Yeah? And there's a third point that I think relates most closely to what I mean or we mean in from a dynamic systems perspective with out of domain generalization, namely that we sometimes are able to even predict into novel dynamical regimes. Yeah, so we are certainly able to do that with a very good scientific theory. Yeah? So, for instance, even if we have built a scientific theory of nervous tissue only based on healthy tissue, biophysical theory, let's say, then by changing some of the parameters, we might be able to predict a transition into a novel dynamical regime like epilepsy. And I think these are all points that are currently really lacking from any AI system. Okay, so how does AI deal with non-stationary environments? So at the moment, I think there are two basic strategies. So continual learning is also a long standing topic in machine learning. Yeah, so also since a couple of decades, people are working on that. And there are basically 4 or 5 fundamental strategies for dealing with catastrophic forgetting. Yeah, so the one is simply prevent strong parameter shifts or do allow for parameter shifts only in directions that don't destroy the already learned representations. Yeah, so in directions which are sort of orthogonal to that. So elastic weight consolidation is one of the, I guess, most famous strategies in this direction. Then there are architectural solutions. Yeah, so low rank adaptation, I think, is one of the most common strategies of fine-tuning large language models. So that's a possibility, or retrieval augmented generative models, like architectures that have an explicit memory. Then experience replay has been all over the place for a couple of years now. So it's inspired by hippocampal replay. And I think it was one of the strategies that has been used either, not sure, either in AlphaGo, in training AlphaGo, at the very least in training on these, the Silver et al. Paper 2017 or something, where they trained it on all these Atari games. Yeah? So that is by now an established strategy, I would say, incorporating bits from previously learned tasks while retraining. And then there are also many functional solutions. Yeah? So one paper more recently has been this one by Doher and Rich Sutton and others. So this illustrates actually one of the benchmark tasks they are using in this community class incremental learning, where they introduce across successive sets of iterations, novel class that are trained on top of the previously seen class discriminations. And conventional backpropagation would just decline over time, while in this paper they developed an algorithm that had several components to it, but one of the most important components was that they reset units which contributed only little to the activity or the performance of the other units. Yeah? So they reset all their weights, and they call it the continuous backpropagation. Okay, so there are many continual learning solutions, but most of them don't really address this problem of quickly adapting to novel environments. Yeah, so continual backpropagation alone wouldn't give you that. But then there's also in context learning and associated strategies. You had a question.
No,
You
no,
want,
I'll
yeah.
wait until I'll wait until this segment is done here.
Okay.
Yeah.
So I think so in context learning, I now mean in a very broad sense. Yeah. So any method of prompting, actually. Yeah. So or chain of thoughts prompts, for instance, you might want to subsume under in context learning in a sense. But in a classical in context learning task, the idea is you if you do that from scratch, people have done that to get to the bottom of what underlies in context learning. So you would present a couple of examples like input-output pairs, and then you would present a probe item. Usually this is done with transformer. So the transformer would be tasked with predicting the output, and then you would train them on a couple of these data. But then during testing, you take some function that comes from this broad general class, like for instance, a class of linear regression models, or also nonlinear regression models. And then you would take a new function, and then it turns out that often surprisingly, these algorithms can predict, do a fairly good job on these items, on these new function classes, which at first glance is almost somewhat mysterious. And so one famous paper is by Garg et al., which appeared in Europe a couple of years ago. So they showed, for instance, that in context learning, in transformers works almost as well as training regression model from scratch by least squares. Yeah? So it recovers the optimal solution, so to speak. Now, this whole idea of in context learning, I think, is hotly debated. Yeah, so it's currently still not clear what's truly underlying this ability. There were claims earlier, a couple of years ago, that transformers might learn some form of in-context gradient descent, and that might explain it. I think this is this is more or less refuted by now. It's not compatible with many of the empirical observations, and there are also some theoretical arguments which speak against it. So, in my mind, it's still not completely understood what's underlying this capability. Yeah, so this is a little bit of work from our own group that I just sneaked in at this point. Yeah, so in context learning, you can even do with dynamic systems. Yeah, so it's a recent
Hmm.
architecture that we designed where you basically can just give a time series snippet, and then without any retraining of parameters, the model would infer the future trajectory in state space, the power spectrum, and some dynamic system properties. And if I have time, I will come back to that in the end.
Hmm.
Okay.
Wait, I think there's one more important category that I don't know if any of the ideas you mentioned actually captures that. What do you think about the new resurgence of these test time training architectures where they have some parameters of the neural network that are never really truly frozen, and they just keep continually doing gradient descent on some maybe like self-supervised objective or something. And this is interesting because now these architectures have these fancy names like test time training, TTT layer, but it actually is more like a more standard pre-deep learning machine
Yeah.
learning. So, what do you think about those architectures?
Yeah. So in my mind, they would fall more or less into that class of continual learning strategies. Yeah.
Hmm. Hmm.
So I think they are not so fundamentally different in my mind. Yeah. So, but I should mention that
Yeah.
I'm not a full expert in this domain.
Yeah, I think you would enjoy those because they are actually just because they're doing gradient descent.
Yeah.
Then you can frame them as dynamical systems. So I think they got that right. I guess.
Yeah.
Yeah.
Yeah. Yeah. Yeah. Yeah. Okay. So then I guess the big question is, how do animals do it? Yeah. So do they do something different to deal with non-stationary environments? And one other question in this context is, how could you even study this in animal? And actually, I want to make a point for that we should aim to align animal tasks as much as possible to machine learning benchmarks or the other way around. Yeah, so I think we can profit a lot of that. And I'm not aware of many people who have done that already. But so let me introduce some tasks which I think already sort of get into this direction. So one is from Sarangpini Show and Jonas Sauers. They are collaborators of ours in a neuro AI project. So they designed a task which is actually quite similar to class incremental learning and continual learning. Yeah. So the animals had to they learn new classifications on each day. So these are olfactory tasks. So they are monitored. There's calcium imaging through these miniscopes across multiple days. And then once in a while, they revisit previously trained discriminations. Yeah? So it's a fairly similar to a class incremental design, you might say. Yeah, and animals can do that actually. So you can see it here. They fairly quickly recover the previously learned classification. So it basically illustrates they must have some mechanism to prevent catastrophic forgetting. So they come back to it fairly quickly. And actually, you see that also in the neural responses. Yeah. So these neural responses are actually quite stable. There are neural representations of these different categories, actually quite stable over many days, despite all these intervening classes. So it's also something similar to in context learning in animals. So this is another task that has been frequently used by another collaborator of mine, Bruno Averbeck at the NIMH in Bethesda. So they are really interested in, I would say in Bayesian inference in animals and in reinforcement learning, things like this. They mainly focus on prefrontal cortex, striatum, and adjacent areas. And they often use these type of N-arm bandits. Yeah, so this is a 3-arm bandit task where there are different stimuli which are associated with different reward probabilities. But the thing here is that every 20 or 30 trials, a new object is introduced and one of the previous objects is kicked out. Yeah, so the animals basically have to constantly adapt to these new contingencies or these novel objects. And what you see is that the animals usually, so this is done in monkeys, they explore the novel objects, but then they start switching to the best option again. And they do that fairly quickly within 20 or 30 tries. Yeah? So that again is sort of evidence that animal can learn these switches in fairly short time, I would say. There are also similar tasks that have been run with rats or rodents more generally. So this is something from Thomas Klausberger's lab in Vienna. There are also a lab with whom we are collaborating on these types of tasks. So in this task, so it's almost like a rodent version of the task that I just have shown you. So there are two different arms. One they call the safe arm, where you always get a low magnitude reward with, but it's certain. And one arm they call the gamble arm, where you get a high reward, but with some low probability. And now these probabilities are systematically changing across blocks of trials. Yeah? So it's in spirit, it's very similar to the task that I have just shown you.
Sorry, could you just clarify for me? So, right, so obviously for these sorts of tasks that Bruno and other people do, right, they often will fit them with, for example, model-free reinforcement learning models that are like, sort of like squarely within things that we understand how to do from a ML perspective, even like quite basic. So, in what sense do you think of this as like getting us beyond where the ML frontier is in terms of something like either in context learning or continual learning?
Yeah. So there are two reasons I'm introducing this. Yeah. So first of all, I want to bring across that there are tasks in the neuroscience literature. If you think closely about them, they already share these characteristics of in-context learning. I mean, we don't know how animals do it. Yeah. So it might be continuous learning or continual learning, or it might be some form of inference. Yeah, so Bruno would claim it's a form of inference. Yeah, so they see these input-output pairs, yeah, where the outputs are the reward signals, and they see sequences of that, and from that they need to infer the underlying rule. But I'm really getting into more detail about this with some examples from what our group has been working on, especially a couple of years ago, or a number of years ago already, the Jeremy Siemens group in Vancouver. And there I get more into why I think this is different from what is happening in machine learning algorithms. These are rule switching tasks. So the animal is facing some rule, and then unknown to the animal task, for instance, in this example, it's a classical operant conditioning rule. Now, so the animal has to press a lever associated with a cue light. But then after a couple of trials, the rule is switched unknown to the animal. And most commonly, it's switched to a rule that the animal hasn't seen at least in this experiment. Yeah. So, for instance, in this case, in these old experiments done in Jeremy Siemens' group, they switched to a spatial rule where the animal then had to only stick to one of the levers. And so, what sort of surprised us at the time is that if you look at the single animal behavior across single trials, then this is almost never gradual. Yeah? So it's almost like there's almost something like a step change. Yeah? So really within 2 or 3 trials, the animal switches its behavior. And so we would claim that the gradual learning curves that often have been observed are some sort of artifact of averaging. And we are not alone with that view. So at the purely behavioral level, that has been pointed out, previously, for instance, by Randy Gallis's group together with Peter Latham. He did a couple of publications where they also published similar observations at the behavioral level. So at the time, then we went back to the neural population representation. So somewhere in this transition period from one rule, let's call it the visual rule, to the spatial rule, the population trajectory would switch over. And the question now is, how does it happen? And the answer is, in many of the animals, that happens also rather rapidly. So these are states identified by a hidden Markov model. And you can see this is an example of a rather steep transition to a new population state. And there are different ways to quantify that. So as I said, this was done at the time by a hidden Markov model. But one technique that we used at the time are these Q-sum plots. So the cumulative sum of differences of my population state to the mean, to the grand mean. So that would first decline and then that would ramp up again. And the steepness with which that happens and the total change you get here is an indicator of the steepness of the rule change. And then you can, for instance, do bootstrap tests on that. There are also animals which we have seen at that time that seem to have some intermediate states. So they didn't switch to the final rule state right away, but there was this intermediate period of uncertainty, which we now believe might be something like an exploration phase. And even associated with that, you often see two of these change points. So, and more generally, we did that for a number of animals, and we saw that these change points, you can do that now with both the behavior and the neural activity, and these change points at the neural and behavioral level often tightly aligned. So there was a very close correlation between these. At the time, we found that two animals didn't adhere to this tight correlation rule. But when we looked more closely, then we found that one of the animals actually didn't learn the task at all. And in the other one, there simply was no detection of change points in the neural activity. So this is sort of a message on the side that I think it makes a lot of sense. It can be valuable to look at specifically those animals which fall out of which leave the pattern that you observe. Okay, anyway, you might want to think of a simple explanation, a theoretical explanation for that. It's related to phase transitions and bifurcations. So think of a simple population level model of neural activity. So this is just a two-dimensional state space, very simple model, where I have drawn the null clines of the inhibitory population, that is a set of states where the derivatives vanish, and the null cline of the excitatory population. And then, as many of you might know, if you now have changed some parameters of the system, or if you have some external input to the system, then you might derive the system through bifurcations. So in this case, it would be a saddle node bifurcation. And then as you increase, let's say, the external input, then you would drive the system through another saddle node bifurcation. Okay, so the bottom line I want to get to is maybe a simple idea is that you have this evidence accumulation for different rule sets in some areas which drive phase transitions in the prefrontal cortex. So as you ramp up or as you accumulate evidence, at some point you might drive the system through such a phase transition, and that might explain why these transition and prefrontal cortex are really so rapid and suddenly. Okay, now more recently, Florian Behner revisited this whole topic, starting with these experiments in our group, but now has his own group on it. At the time, we decided to extend the rule set. So we introduced novel stimuli, like for instance, acoustic stimuli and on top of the house lights. We introduced more rules into the task. Yeah? So in fact, in this version, there were 8 different rules now. And the idea was to study, so a hypothesis that we had from the previous studies was that the animals don't really learn these stimulus response reward associations, but they really learn rule sets. Yeah, they form hypotheses about the currently active rule, and they follow different behavioral strategies, and then they switch between different behavioral strategies. So that's what we wanted to test in more detail with this type of task design. So there were 8 different rules defined. Some related to the acoustic stimuli, like go silent or go click, or related to the light stimuli, like go dark or go light. But there were also rules defined based on the animal's reward experiences, yeah, like this wind shift blue stay, yeah, so which is sort of a natural strategy that actually rodents or rats in particular often have, yeah, or alternate. Yeah, so once you won on a certain option, go to the other option. And then we identified these strategies with a simple binomial test. Yeah, so for every 10 sets of trials, we just counted how many of the trial outcomes or behaviors of the animal are consistent with different of these rules. And then we just took the binomial distribution to test for significance. Now, very simple statistical test. Okay, and one of the observation was, like in the previous task, that there were often these rapid shifts between the different behavioral strategies. And also there were different neurons which account for these different behavioral strategies. And one aspect that is interesting that we already observed before is that this coding for strategy is actually very prominent in prefrontal areas like the infralimbic or prelimbic area in rodents. Yeah, so it's and it's present all the time. Yeah, even in the intertrial intervals, and even before the first cue has been shown. Yeah, so strategy encoding is apparently something that is very that is very salient in frontal areas. So then there was another interesting observation by Florian Behner and Hazem Tutunji, who developed a series of reinforcement learning models for this task. And that is that the animals are often, before the animals switch to a new behavior strategy, they switch their attention. Yeah? And that you sometimes can read off from the angle that the animal has to different stimulus modalities. Yeah, so for instance, to the house light. And so you would find that before the animal switches from a strategy that is driven from a behavioral rule that is driven by the house light to one that is focused on the auditory cues, it would change its angle to the house light. So that we took as an indication or as a measurement of basically of an attentional focus. And of course, attention somehow restricts the subset of rules that you need to consider. Yeah, so it's like a filter on the behavioral strategies. So Hazem then used different reinforcement learning models, actually quite simple models, all inferred from the animal data, from the actual behavioral data by maximum likelihood. They differed from, let's say, the most fundamental models by 2 different things. So first of all, there was a weighting of the values as well as a weighting of the learning driven by the attention. Yeah? So these weights were estimated from an attention score that was derived from the actual behavioral observations. So attention played a big role in these models. And the other thing that we studied or investigated is models which considered values assigned to whole rule sets versus models which assigned values to specific stimulus action pairs. And as you can see from this graph, the models which worked defined on rule sets and which acknowledged attention had the highest likelihood scores. Moreover, they were the only ones which could reproduce these sudden changes in the behavior of the animals. Yeah, so if you only had attention to in the learning phase, these are actually the color curves here are estimated from the behavior. So these curves here in black are the ones from the models. So they wouldn't be able to reproduce these sudden switches. As would be any of the rules which just worked at the level of stimulus action associations. Okay, and then there were a couple of interesting transfer effects. Yeah, so for instance, if animals that were already previously trained on a rule, they switched more easily. They had a change point much earlier during a sequence than animals which were native. Right, or for instance, if you just have a random rule in place, then animals which were previously trained on a set of rules, they would test certain these previously trained rules more early during these sequences. So I think what is kind of interesting about this is it has sort of a relation to a training set that you train machine learning models on. Yeah, so I think it's something interesting to investigate or to acknowledge. Yeah, so both animals and AI systems are trained on certain training corpora. Yeah, and so it might be interesting to study more systematically how does the behavior depend on this training corpora, both in animals and in AI systems. Yeah, so in animals, I think it hasn't been done to a large extent. Yeah, but essentially in this task, we observe both positive and negative transfer. Yeah, so sometimes animals would perseverate on rules that they have previously encountered, but sometimes these rules would also facilitate the transfer to neurons. Okay, so this is basically what I wanted to show with respect to context learning and rule learning. Well, there's one more bit that I find interesting. It's also from a it's based on a study that was also happening at our institute. Eleonora Russo analyzed the data at that time, which was on extinction learning. So I think it's interesting that even in extinction learning, you often find these very sudden switches in the behavior of the animal. Yeah, so this is basically the response that the animal does, so each tick mark here is a response or a no response, and you see that there's a relatively sudden transition in the behavior of the animal, even during these extinction trials. And again, they tightly correlate with change points in the neural activity. Yeah, so maybe here at the bottom right, it's one of the most prominent examples. So one of the neurons would basically just stop firing at some point. Yeah. Okay, so let me just wrap up some of the observations that I personally find interesting about animal learning. Yeah, so the first one is that rule learning happens really within a couple of trials. Yeah, it doesn't take a long time for the animal to switch between different rules, and it seems to be based on a systematic testing of different strategies. Yeah, so animals don't really gradually learn as, let's say, at least classical behaviorist theories would have it, but they seem to systematically test different behavioral strategies. Another interesting point, I think, is that animals continue to explore even when they already have perfectly learned the new rule. Yeah, they would once in a while switch to the old or to the other options. And that's sort of I would say an inductive prior, which makes perfectly sense in a non-stationary environment, yeah, because things might change. And another thing that might be worth pointing out is that performance, of course, heavily relies on previously learned task elements. Yeah, and in fact, neuroscientists would use that in procedures like shaping. They would first familiarize the animals with the different elements of the task. And I think it's also worth noting that extinction is not forgetting. It's not unlearning something previously learned. It's the animals actively suppress what they have previously learned. And there's a lot of evidence for that. So the bottom line is a bit that I think in opposition or in contrast to how most machine learning or AI models are currently trained, learning in animals is a very active and a very compositional process. So that's sort of one of my basic baselines here about the observations in animals. Any questions
Great.
about this?
Yeah, I have. So it's very interesting that all of this evidence that you synthesize in this talk, and I think the resulting conclusions make a lot of sense. But I wonder if you can speculate a little bit, maybe about what are the underlying mechanisms. So for example, like you say that. Okay, that's gone.
Okay, let me go ahead. Yeah? So truly, we don't know. Yeah? So I think we don't really know what is even continual learning and what is inference during these tasks. So there are a couple of ideas that I find quite nice. Yeah. So this is a paper by Wu and Maas. So that it's nothing of our own work, but I find it kind of interesting. It's based on this observation in Jeff McGee's group about this behavior timescale plasticity. So that I find very exciting. So I mean, I would guess that most of you know that synaptic plasticity is happening at all different timescales, which is in itself interesting. But this behavior timescale plasticity is something that appears could account for a lot of older observations that even early behaviorists like Torman made. Yeah, so Torman termed this incidental learning. And I think all of us know that for instance, if you are in a new city, and we just explore it, even if it's not a new city, so I can recall many details of my day yesterday, although I was not explicitly rewarded for them. I can tell you almost literally how I got home and what I encountered on my way home. And this is sort of surprising, because it has nothing to do, I would say, with reinforcement learning. So Torman termed that incidental learning, and that might be related to behavior timescale plasticity. This is just a conjecture. What they meant by this is a mechanism where so it's observed first in hippocampus, I think in CA1. Where they observed that neurons would produce these plateau potentials in the dendrites. And if there are inputs roughly within a time frame of a couple of seconds, then they would be amplified. Synaptic rates would be increased, long-term potentiation. While if they are out of this time window, they would undergo long-term depression. I think one of the interesting things is that that these changes happen with one or two exposures, so that they are really quite rapid. So this was nicely formalized and simplified in this paper by Wu and Maas. And they sort of showed that you can use it as an alternative mechanism to Hopfield networks for imprinting memories very quickly in a much more, let's say, computationally efficient way. So they could store many more patterns than you would be able to do in a classical Hopfield network. So it's not really my work, and I don't want to go into too many details about that, but I think at the synaptic level, this is a highly interesting mechanism. But of course, you might also want to think of dynamical mechanisms. So I think many of you are familiar with this concept of a line attractor or manifold attractor. It's all over the place in the recent 10 years in neuroscience. Yeah, so it refers to the fact that so what we mean by that is that you essentially have a continuous sheet or manifold of fixed points or equilibria, and wherever you start outside of this manifold, which is just this line in this two-dimension example, you would converge to this manifold, and then you would just stick there. Yeah, so it's sort of a even 20 years ago, there were these ideas by Sebastian Jung and others about how the goldfish can keep its eyes stable. And one of the hypotheses was underlying that is a line attractor. Yeah, and in working memory, how can we retain a gradual memory? And one idea would be a line attractor. You can also detune a line attractor slightly. That would give rise to something like a slow manifold. And that's actually a mechanism you can exploit in machine learning. Yeah? So you can exploit it to realize or to imprint many different timescales into a dynamic system, even without explicit biophysical time constants. Yeah, you can do that with a classical recurrent neural network. And by that, you can learn systems which evolve on many different timescales. But maybe most interesting in the current concept is this concept of ghost attractors. I think it has originally been introduced by Suda, but has been sort of revived by a couple of colleagues in Bonn who showed that basically you can have these change of ghost attractors. So first of all, what is a ghost attractor? So ghost attractor is an object which is not quite an attractor anymore, but it just lost its stability. But because it just lost its stability, there's still this slow manifold or this region where the trajectory would go very slow. But then at some point it would leave that region again. Yeah. And so you can have something, you can change these, put these objects into a chain. And the interesting thing about it is, I think, because these ghost attractors live close to a bifurcation, you can very easily and quickly rearrange these chains. Yeah. So even any slight perturbation, in short-term plasticity or by neuromodulation might rearrange these configurations. Yeah? So these configurations, I would say, are sort of dynamic setups which can be very quickly and easily adapted to novel environmental configurations. Yeah? And that's what I personally find quite interesting about them.
Can you help us understand the concept of attractors in machine learning? So should we think about these as depicting or illustrating the inference dynamics or the learning dynamics or both? Does it apply to both?
It might be both. Yeah. So I think there are many ways in which you can change attractor landscapes. Yeah, with that attractor, I really mean in the classical dynamic system sense as a set to which you converge in state space and which has its basin of attraction from which you converge to the set. In this sense, the line attractor is an attractor. Yeah? So you converge to the set and then you remain within the set. You can think of it as characterizing the learning dynamics itself. Yeah, so learning dynamic itself might be described in terms of a system converging to certain attractor sets. But you might also want to think of it as the system of the state on which activity evolves, neural activity, which then in turn can be changed either through learning itself or through other faster plasticity mechanisms or just things like neuromodulation or external inputs from the outside world. I think for me, the most important thing about this year is really about this ghost attractor idea is it's per se a configuration which is very accessible to quick reconfiguration because it lives close to a bifurcation.
Makes sense. Thanks.
So it's close to a critical regime.
Mm-hmm.
Okay, and then you find evidence for all of this in the nervous system. Yeah, so line attractors, I think, have been heavily discussed throughout the last 20 years. It's also interesting that many neurons in many areas, cortical areas, or even subcortical areas, can sort of adapt their activity fairly quickly, the time course fairly quickly to temporal intervals that we observe. And there's also maybe some evidence for something like ghost attractors. So this is from an older study, again, in collaboration with Jeremy Siemens and Christopher Lapash, who's right now in Indianapolis, where we observed, for instance, that so this was during relatively complex radial arm-maze tasks with delay, decision-making tasks, multiple item working memory, and decision-making tasks. And one of the observations here is that as you move into new task phases, the vectors would be fairly long, yeah. So there would be a high vector velocity, and then it slows down. The state slows down and slowly moves through this task period, and then quickly moves out again. Yeah. So as you move to the center of the task, the vector velocity would slow down. So this might be some indication that something like you could explain it with a chain of ghost attractors. Let's put it this way. Okay, so this basically ends the major part of my talk. So the basic take-homes here from my side is natural environments as well as brains are complex dynamic systems. They both evolve on many different timescales, and I think it makes sense to view brains to a certain degree as somehow synchronizing or extracting environmental dynamics. Animal learning is an active and compositional process that I think is often more guided by inference and insight rather than this automatic, gradual, behaviorist style of learning. There are interesting fast plasticity mechanisms like this behavioral timescale plasticity, but there are also interesting dynamical mechanisms like these ghost channels, which might somehow support these processes underlying in context learning and continual learning. And I wanted to make this plaidoyer for designing neuroscience tasks much closer in spirit to benchmarks that we are also using in machine learning and vice versa. Yeah? So yes, so this would be major take-homes from my side for the first part, but I have a second part if you are still alert and interested.
Oh, definitely. I guess we still have almost an hour left, so it's up to you if you have time. We would love to hear the second part, but maybe before doing that, this is great. That the take-home messages, I think, I would, it would be interesting to spend a little more time here. Um, let's think about how we can turn these take-home messages into actionable advice for designing machine learning algorithms and architectures. Let's suppose that somebody in the audience here, or maybe like in the future, somebody in YouTube audience, does not know much about neuroscience or experimental neuroscience, but they want to actually draw inspiration from neuroscience or these take-home messages to apply them to machine learning. Can we actually go one by one and then together try to turn them into these actionable advice?
Mm-hmm.
Yeah.
Yeah, so that's a very good question. I mean, we have sort of case studies for that. Yeah, so
Yeah.
for instance, our group had an iClear paper 5 years ago where we basically used this idea of a line attractor and detuning the line attractor to equip a recurrent neural network with the capability of learning multiple timescales simultaneously, without knowing anything about the timescales and the data, and without any explicit inductive bias. So I think for the dynamic systems concepts, in a sense, it's easier. Yeah, so you can think of mechanisms like regularization terms that you include in recurrent neural networks that would try to keep a neural network close to, let's say, a ghost attractor configuration. Yeah, and by doing so, you might want to keep the network in a regime that is very sensitive to changes, rapid changes in the environment. So that might be possible and feasible.
Wait, actually, okay, before moving on, let's explore that a little more. So, um, the concept of ghost attractor, my very high level understanding is that it's interesting because it keeps you close to some bifurcation point and it allows you to quickly change configurations and go from one attractor to another. I don't know if that's accurate, but that sounds very abstract, and I wonder if we just like make it a little more concrete in the context of just a normal standard recurrent neural network. How can you turn that into a regularization term? Is that straightforward? Like, how do you do it?
It's not necessarily straightforward, but
Hmm.
a recurrent neural network is a dynamic system itself. Yeah, either in discrete or
Yeah.
continuous time, it's a dynamic
Hmm.
system.
Hmm.
So you do have attractors in there. Yeah,
Hmm.
you always have attractors. Yeah, otherwise your system just diverges. Yeah.
Hmm. Hmm.
Um, so um, so this is about tuning these attractors in the right way. Yeah, and
Hmm. Hmm.
so the um, the tuning would go in such a way that you try to keep it close to yeah, I don't have a, I think I didn't bring a graph on that. I didn't bring a figure on that, otherwise it would have been easier. Um, you so let's start with the manifold attractor configuration. Yeah, so
Hmm.
you 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 can put a regularization term that
Hmm.
pushes a
Hmm.
subspace or a subset of the units towards the manifold attractor regularization,
Hmm. Hmm.
but you
Hmm.
wouldn't strictly enforce it. Yeah, so you wouldn't go all the way to a manifold
Hmm.
attractor,
Hmm.
but you would the regularization would push it into that direction. But
Hmm.
otherwise, this object is still subject to all the learning and the computation that the network wants to do. Yeah? So you would,
Hmm. Hmm.
by such a mechanism, you would automatically sort of push one of the attractors or attractor configuration in your system
Hmm.
toward a ghost
Hmm.
attractor.
Hmm. Hmm. Is that fair to say that, if you write down this explicit RNN dynamics equation, you would just add other terms that would encourage such behavior to that equation?
Exactly. Yeah. So yeah,
Okay.
if
Hmm.
you yeah, so it's literally so in that order study we did it literally by a regularization term. Yeah. So a
Oh,
regularization
okay.
term which tries on the way on all the weight parameters of the network. Yeah. So it pushes the
Hmm.
net
Hmm.
weight parameters in a way that induces slow temporal behavior along some
Hmm.
dimensions.
Great. Okay, so that's one lead. I want to explore this other concept of compositional because I think that's a very interesting idea that probably one of the important ways brains and machines diverge. My understanding of compositional is maybe a narrower definition coming from vision is that, if you want to understand a scene, it is composed of different objects, and if you understand those modules, whatever, things in isolation, then you can compose them to get to understand novel things, novel combinations. Uh, is that the sense in which you're referring to this compositional process, or is it more general than that?
Yeah, both. Not quite certain about the answer. So what I mean is that you sort of learn behavioral primitives. Yeah. So you
Uh-huh.
learn to respond. You learn how to grab things and to manipulate them, and then more complex behavioral strategies are sort of built from these more primitive motives, behavioral
Hmm.
motives.
Hmm.
And
I
I think
see.
that's reassembling these behavioral motives is something that works much quicker than,
Hmm.
of course, relearning everything from scratch.
I
And
see.
so my colleague
Okay.
Bruno Elverbeck, so that type of input in that paper was by him as it would be that much of that is what is development is about. Yeah, so it's
Mm-hmm.
building up these different levels of motives that
Mm-hmm.
then can be reassembled into new forms and strategies.
Mm-hmm. All right. Thank you for clarification. Before moving on to the next section, is there any other questions from the audience?
Yeah, I have one about this fourth point here. Um, I'm wondering if you can just give some more specifics, because I mean, or I don't know, for example, my guess is that if you tested an out of the box LLM on something like these, bandit tasks that we give animals, that they would be able to do it no problem, that there would be some emergent and context learning strategy that would allow them to, at least approach animal behavior, if not optimal behavior. So I guess my question is, have you done that? Is that the kind of thing that you have in mind for these common benchmarks? Or like, if not, what would be maybe like a stronger benchmark outside of, I mean, I think that sort of like robotics is like one obvious example where there's still a lot of progress to be made, but in these sort of more cognitive domains about rules and sort of state switches.
Mm. So first of all, I meant more along the lines, for instance, for the continual learning task. So I think it might be the more interesting thing might actually be the other way around. If you design a continual learning task, which I think you can easily do for animals, which is almost one-to-one machine learning benchmark. I think this is very doable. With your point about large language models, so why would they be able to do it? Probably because it's somewhere already in their training corpus, I would claim. And probably would be able to refute that. Yeah, because we don't know the training corpora of these models. They are trained on everything that is out there. Yeah, so it's very difficult to test really what's underlying in context learning in large language models or in transformers. And that's why people in this field went back and trained them from scratch on certain function classes. Yeah? And even there, it's already complicated. Yeah? So I think we don't really have a good idea. So it might be true that a language model could do it, but then the question is, why could it do it? Yeah? And can it do it only for these specific tasks that I have shown here and which are already on the internet somewhere? Or can we design new tasks, which are not on the internet yet?
Hey,
Yeah.
thanks. Maybe I guess now let's proceed to the second part.
Okay. So this is a bit more technical.
Mhm.
So this is what we are mostly doing these days. As I think was apparent throughout the first part of the talk, we are interested in a lot in dynamic systems, and actually we are interested in AI or machine learning algorithms which can reconstruct dynamic systems from data. Yeah, so we want to learn dynamic systems from data. So what do we mean by that? So usually we have access to time series observations from dynamic systems, but we don't have access to the dynamic system itself. Yeah? And many dynamic systems out there in nature, the most interesting ones are fairly complex. Yeah? So even any biophysical model we have is only a crude approximation to that system. Now, so we assume that there are some dynamic systems underlying our time series observations, but we don't know them, and we want to reconstruct them from data. So we want to be able to train some device, most commonly something that is a universal approximator of dynamic systems, like recurrent neural networks, for instance, are. And then after training, we want to be able to generate new data from that device that agree in their geometrical and temporal structure with those produced by the originally observed system. So that's our goal. More specifically, we are interested in some form of generalization we also want to have. Yeah? So this is an example of the the famous chaotic Lorentz attractor, probably the most famous chaotic system of all time. I don't know, I assume everybody's familiar with that. If not, please raise your hands. Which is shown here. So there are different trajectories starting from different initial conditions converging to this chaotic attractor object. And in yellow, there are the different equilibria that coexist with this chaotic attractor. Now, in practice, we only have access to one trajectory, finite time trajectory, of course. Yeah. And so the question is, can we reconstruct really this whole chaotic behavior and ideally other objects in the state space just from this observed trajectory bit? And sometimes you can actually do this. Yeah? So this is an actual recurrent neural network reconstruction, which was just trained on this trajectory bit and which correctly infers, for instance, in this case, not only the chaotic nature of the attractor, but also the equilibrium. Okay, so there's one important point in this field in my mind, and that is if you wanna, so how do you evaluate the dynamic systems reconstruction? Yeah, so I think it's very important that you cannot use out of the box mean squared error things, for instance, yeah, because if you have a chaotic system, then trajectories will very quickly diverge, yeah, and 99% of complex dynamic systems are chaotic. So you need other measures. And measures that we are commonly use are either based on the agreement in state space geometry. Yeah, so this is the state space here is a type of Kullback-Leibler divergence defined in the state space. Yeah, so it gets smaller the more closely our reconstructed attractor agrees with the true object. You can also assess power spectra. Yeah, our interest is often more in long-term temporal properties because, as I mentioned, on the short-term, trajectories will quickly diverge. And then there are other dynamic systems measures you can use, yeah, like Lyapunov exponents or measures of the fractal geometry of the underlying objects, things like this. Yeah, so the bottom line here is a bit that common statistical measures, often are not the only thing that you should use. They can sometimes be heavily misleading. And we need to, if you want to assess the quality of a dynamic system reconstruction, we need other types of measures. Okay, so what our group is specifically interested in is models that we train on data that are mathematically tractable, because we come from the perspective of scientific machine learning. So we want to have models where we can actually analyze the dynamics, which are not so complex in their own right, which are not black boxes, but which are accessible to mathematical methodologies. And so the easiest thing are linear dynamic systems. Yeah? So that those can be completely characterized mathematically in analytical closed form. But most systems we are interested in are unfortunately not linear dynamic systems. Yeah? They are nonlinear. And so the idea a bit is that piecewise linear dynamic systems or recurrent neural network are the next best thing. Yeah? So they are defined by different linear subregions. Yeah? So, and quite natural nonlinearity that gives rise to a piecewise linear system is just a rectified linear unit. Yeah, like this. If you just take this max over over 0 and z. Z is an activation state here. So this describes a simple piecewise linear recurrent neural network. It has this autoregressive linear term, and then it has this piecewise linear term with the weight matrix W. It might have bias terms, external inputs, maybe noise terms. Yeah, but what makes it piecewise linear is this rectified linear unit. So over the years, we developed different flavors of these models. I think it's, I don't want to go into all of this, but the idea is that we wanted to increase expressivity of this class of models while still keeping them piecewise linear. And I should mention that actually a lot of dynamic system theory was built on piecewise linear models. Yeah, so they are very famous in dynamic system theory. Yeah, so if you think of the tent map, for instance, And also in engineering, piecewise linear systems have been very popular for decades. So one of the maybe more interesting bits here is these what we call almost linear recurrent neural networks. So these are networks recurrent neural networks, which are almost everywhere linear and only include as few ReLU-based nonlinearities as possible. Yeah? So we'll try to be as parsimonious as we can. Okay. So one
Can I ask
important.
you a question about I think this goes back to the evaluation of like what is a good reconstruction, and also as well as whether a parametric model like this could be identifiable. So is that something that you're concerned about? I don't think that's actually a big concern, because probably in this approach of reconstructing dynamical systems from observed data, you want to actually do something with the reconstructed model. You want to study it, or you want to predict something with it. So in that case, maybe identifiability is not an issue. But I wonder what are your broader thoughts?
Yeah.
Whether you get the exact parameters correctly, does it
Yeah.
matter? Yeah.
No, so identifiability in terms of parameters is not important, I would say. Yeah? So
Okay. Hmm.
what is important, of course, is that we get the same topological structure and geometrical
Hmm.
structure. That's important to
Hmm.
us. And
Hmm.
this is still an evolving field, I would say. Yeah. So it's a
Hmm.
yeah. So, but what we use at the end of the day are these dynamic systems reconstruction measures that I introduced
Hmm.
previously.
Okay, so this makes, I guess, the finding those or deciding your reconstruction measures, the measure of success, almost as important as the actual method, I guess.
Yes. But there is sort of an established theory
Hmm.
in there are certain things that are important in dynamic systems theory. Yeah? And
Hmm. Hmm.
this is, for instance, the topology and geometry,
Hmm.
fractal dimensionality of attractors, for instance. Yeah. And so these
Hmm.
things
Hmm.
you can also infer from empirical data.
Hmm. Hmm. Perfect. Thanks.
Okay, so one point that I want to stress is that out of the box, backpropagation through time or things like this don't work for dynamic systems reconstruction. You need specific training techniques because these training techniques need to sort of emphasize the long-term behavior of the underlying systems. And it's related to other problems that we have in training recurrent neural networks, like this famous exploding and vanishing gradient problem. So if you unwrap a recurrent neural network in time, so that's what backpropagation through time essentially does, and then it backpropagates the errors across layers in time, and that easily leads to explosion or the vanishing of gradients. And more importantly, you cannot avoid this problem when training on chaotic systems. So this becomes a bit formal now, but maybe let me just convey the gist of it. So if you look, so chaotic system is defined by one of its Lyapunov exponents becoming larger than zero. So the Lyapunov spectrum is given by the product series of Jacobians in a discrete time system. Yeah? So the Jacobians are the matrices of second derivatives of my recursive function or map with respect to all the states. If you have the product series of that and take the logarithm of the geometric mean, then the Lyapunov spectrum is defined over this. Yeah? So the maximum Lyapunov exponent is defined as the norm of this matrix object. And so for a chaotic system, we must have it to be larger than zero. So this is defining for chaos. And that's also the reason why you have divergence of trajectories. Yeah, so nearby trajectories will always diverge. So the crucial observation here is that the same product series of Jacobians occurs in the loss gradients. Yeah, so, and by that you can then infer or deduce that you will always run necessarily in this exploding gradient problem. Yeah, so and over the last years we have dealt with different training strategies. So this is work by Jonas Michael and Zara Monferret. a couple of years ago in the group. One of these techniques we call sparse teacher forcing. So the idea here is, so ZT is the latent state of the recurrent neural network. The axes here are my observations, and the latent state in the simplest case is related just by linear mapping to my observations. But this could be any type of decoder model. Yeah? And then we construct a control series by somehow inverting this decoder model. Yeah? So in this case, in this linear case, we would just take the pseudo-inverse of the matrix. And then the idea is, okay, once in a while, you replace your true states, or your, sorry, not your true states, but your model-generated states by these data inferred states. But you need to do this in a sort of a with an ideal temporal gap between, so there's an optimal temporal interval between these replacements. And that is actually indeed strictly determined by the maximum Lyapunov exponent. So the intuition behind this is that you need to give the system a bit of freedom to diverge, or to explore the future. And then you need to pull back the system at certain times that are strategically chosen based on the Lyapunov spectrum. So that's the idea behind sparse teacher forcing. So this is an example from that old paper. So if you choose this leg too small or too large, you don't capture the long-term dynamics. You need some optimal interval that is related to the optimal predictability time of the system. So a more refined technique is what we call generalized teacher forcing. It goes back to an old idea of Kanji-Doya, actually, where you take a weighted average of a forward propagated state from our recurrent neural network and a data inferred state. And it turns out there is an optimal weighting you can do. So you can choose this weighting alpha here in a way that leads to, I don't want to go into all the details, but you can choose it in a way that leads to optimal control of the gradients throughout learning. So they neither diverge nor may vanish. And you can actually adaptively choose this alpha during training in such a way. And so these techniques, there are many other techniques in the field, also by other people. Some also introduce into the, as regularization terms, into the loss function, long-term objectives. So for instance, you can actually put that as a regularization term, the maximum Lyapunov exponent, or you can have something else. So that there are many approaches to this. But the bottom line kind of is that to achieve proper dynamic systems reconstruction, which reproduce the long-term behavior, you need something like this. And these are just some examples. So this is on fMRI data. So in blue is a true recorded activity. This is a power spectrum. This is an example of a state space. And in red, it's generated activity. It's simulated. It's not a fit to the data, but it's simulated after training the model on these data. You can do this for EG activity, or you can do this for single units. Okay. So there are a couple of recent developments, and now it depends a bit maybe on in which you might be most interested. So we also advances for multimodal configurations. So for instance, in neuroscience, we of course have observations not just like spikes or calcium imaging. We often have behavioral observations on top, or we might, more generally, might have different modalities that we observe simultaneously. And so we want to, a couple of years ago, Manuel Brenner, Florian has devised a technique in our group that takes on board many of these modalities simultaneously for training some dynamic systems reconstruction model, most commonly in our case, recurrent neural networks. So they did this by a multimodal variational autoencoder, which generates a training signal for the recurrent neural network. And then we just enforce that these two latent states produced by the multimodal variational autoencoder and the recurrent neural network agree by coupling them to the same set of decoder models. So this is a neuroscience example. So at the top is a test set that was not used for training. At the bottom is generated, that is freely simulated activity. The only things that we use from the test set is an initial condition that we inferred. Plus we use the same type of stimuli. Yeah? And this is from open source data by the Bujaki group from rodents just basically running back and forth along this linear track. So the simulated and the real activity agree quite well, as you can see. And statistically, so if you, for instance, compute the correlation between generated and test set activity, then the correlation, so here in blue, is almost as high as if you would correlate different segments of the real data itself. So if you take just the physiological data, you infer different types of spiking statistics like the mean rate or coefficient of variation, and you correlate them with each other, then the correlation is about as high as between the model and the real data. You also, from this, you can also do behavioral predictions, but you also get something like a common latent state, which embeds both the behavior and the neural activity. Yeah? So this is a bit similar to Zebra, only that on top of this common latent embedding, you would get a reconstruction model for the animal, which generates a generative surrogate model, basically, of the neural activity. Okay, we also tried this on these trial-dependent tasks. It relates to what I have shown you previously, but my tendency would nevertheless to skip this for the interest of time, unless you are very curious about this, but then I can come back to this. So let me skip this for now. So one thing that that interests us most at the moment is out-of-domain generalization. And that relates to learning in non-stationary environments. Yeah, so out-of-domain generalization, in our view, has a very specific meaning in dynamic systems reconstruction, because it's not just a distribution shift, but it's generalization to completely novel dynamical regimes. Yeah, so most complex systems, for instance, are multistable. Yeah, the brain is certainly multistable. Hot-field networks are multistable. Yeah, so they have different coexisting attractors. Yeah? And now the question is, can you train on just one of these dynamical regime and then generalize to a dynamical regime that you haven't observed? Yeah? So can you train a model just on healthy neural recordings and then infer behavior in epilepsy? Yeah? So that we find is an extremely important question that is a thing that you would demand from any scientific theory. Can we do that with machine learning approaches as well? Another aspect of out-of-domain generalization are tipping points. Yeah? So as you know, many dynamic systems, as some of their parameters change, will undergo bifurcations. Yeah? So this is actually an example from a spiking neuron model, which has a stable membrane potential, like a locked high potential. Yeah, so if you really excite a neuron very much, then it might get in this high locked state. Where it cannot recover from the excitation anymore. Then here you have a limit cycle. So where the spiking regime, and then you have the resting potential here. So this is an example actually from a bursting neuron model with an underlying slowly varying parameter. And so this drives the neuron through different dynamical regimes. And sometimes models can learn that. Yeah, so this is an example of a recurrent neural network that has only been trained on the bursting regime, but then predicts the transition into this regular spiking regime. But this is a very, generally very important question, yeah, in many areas of research. Yeah, climate science is an obvious example, yeah, where you want to be able to not only predict the tipping points, but you want to be able to predict what happens after this transition. So this is one question we are working on, and one way we are approaching that is through foundation models. So we have developed, this is an example from work by Manuel Brenner and Elias Weber in the group, just from last year, where they worked on a model which is simultaneously trained on many different dynamical regimes. So it has a shared backbone of dynamic systems parameters that are trained on all systems that are observed at the same time. You might want to think of this as different subjects. And then there are a subset of parameters which are subject specific. There are many different approaches, similar approaches around. So at the same conference, for instance, Memming Park groups in Lisbon, they had a very similar approach to this. I think, again, I don't want to stretch this too much. I won't go into too much detail, but this is one approach which you can train on many different dynamical regimes and subjects simultaneously. And then one interesting observation here was that often the system, the single subject features would correspond to control parameters that we have varied in the underlying dynamic system. So you might want to think of this like you now have access to the control parameters of the system, and you might be able to use that to generalize out of domain. So it didn't quite work as well as we would have wished, but right now we have another NeurIPS submission where we have an extension of this model where it starts to work. Okay, so maybe let me go to one of the most exciting models we currently have on the shelf, which we call Dynamics. It was developed by this guy here, Christoph Hemmer in the group. So this is really a zero-shot dynamical systems reconstruction model. So it consists of a mixture of experts. So many of these almost linear recurrent neural networks, and it consists of a gating network, which then, based on a context signal that is just a time series snippet that we give to the model, decides on the weights which the different experts are to be weighted to give rise to an overall prediction. So the interesting things about this is, first of all, we trained it on a fairly small corpus of dynamic systems. Basically, just these, I think, about 30 different artificial 3D chaotic and cyclic dynamic systems. So this is a whole training corpus. So you might wonder, does it really qualify as a foundation model? But based on its generalization properties, it sort of does. So we trained it by the same types of training algorithms that I have illustrated earlier. And it's fairly good in doing out of domain, not just forecasts of time series, but dynamic systems reconstructions. So it gets the attractor geometries often quite well. And these are all examples of systems that haven't been in the training corpus. So they are novel to dynamics, and as well as the power spectra, as well as the temporal structure of the system. So you might say, and maybe just as a note on the side, so this is something that classical time series foundation models cannot do, and they cannot do it at all. So Kronos wouldn't be able to do this. They don't capture, for instance, the true Lyapunov exponent of a chaotic system, because they mostly do context parroting. And they won't be able to capture the true attractor geometry. So now you might say that, okay, this is dynamic systems. This is still out of domain generalization on dynamic systems that are similar to the system that the dynamics has been trained on. So we compared this now to systems that dynamics hasn't seen at all. So these are examples of time series that are commonly used in the time series modeling literature. So for instance, these are data from electrical, so these are empirical data, like for instance, from electrical transformers or cloud requests or traffic data, which are commonly used to benchmark time series foundation models. And the surprising result was that even there, dynamics would often outperform these time series foundation models. Now, both in prediction and almost surely in the dynamic systems reconstruction, in the long-term properties. And this year, with the spike trains, with the voltage data, is one of the, in my mind, most puzzling examples. Yeah? So dynamics has really seen only these 30 3D dynamic systems that I have shown. Yeah? So none of them are even remotely similar to the spiking activity that this real neuron produces. So nevertheless, dynamics was able to predict this to a fairly well degree, I would say. Okay, I think I don't want to overstretch it. I think I will close here and just refer back to the people who did this work. So Florian Hess and Manuel Brenner, who has his own group by now, have been instrumental in developing many of these training methodologies. Zara Montferrat for a long time was our mathematician in chief. So she developed many of the theorems of the mathematical backbone of many of these techniques. Lukas Eisenman and Elias Weber here and Alena Brender developed some of the techniques for analyzing trained models. Christoph Hammer, I already mentioned, he invented this dynamics model. And I think the most important people I have mentioned. So thank you very much for your attention. Very last point. If you are interested working on that, please contact me. Now, or if you are just interested in doing a sabbatical in beautiful Heidelberg, then let me know. Okay, that's it.
Thanks, Daniel. Amazing stuff. Questions from the audience? I actually have one. So your the last result on dynamics, I think that's quite fascinating that you trained this on, if I understand correctly, you had a bunch of synthetic uh, setups in your training set, and it just never saw any of these real data sets, yet it actually generalizes in zero shot.
Yeah.
Okay, I think that's very strong. Can you help us understand why? What is
Yeah.
the mechanism that enables
Yeah.
this?
We're still sort of contemplating about it.
Okay.
We just submitted a paper on to NeurIPS that
Hmm.
dives a bit into this.
Hmm. Hmm.
That paper deals with the simplification of dynamics, where we try to boil it down to the essential
Hmm.
mechanisms.
Hmm.
And I think it has to do something with that it uses the context signal in a very smart way. Yeah. So
Hmm.
in a
Hmm.
sense, Chronos or time series foundation models use it in a, let's say, not so smart way. They are just parroting the signal,
Hmm. Hmm.
while
Hmm.
dynamics achieves to stay close to the context signal while extracting its chaotic signatures.
Hmm.
Um,
Hmm.
yeah, so I wouldn't say we necessarily we haven't completely understood it yet, yeah, but we
Hmm.
got a step closer to it by
Hmm.
understanding the role that the context signal plays in shaping this.
Could it be, I don't know, it's a compositional model. So maybe this is completely naive, but one thing that comes to mind is that any real dynamical system could be maybe composed of certain motifs that are general enough that can be combined in novel ways to get into to reconstruct very complicated dynamics. And what dynamics does is it learns those bases and it learns how to combine them. Is that the idea?
This is yes, this is a very good suggestion.
Hmm.
So um, there is indeed only a finite set of possible topologies in dynamic
Hmm.
systems. Yeah.
Hmm.
So
Hmm.
what can you have? You can have equilibria. They can be stable,
Hmm.
unstable, half stable. There
Hmm.
can be spirals or non-spirals, but that's
Hmm.
it about equilibria. You can
Hmm.
have limit cycles with the same stability properties. You can have chaotic
Hmm.
sets. You can have
Hmm.
quasi-periodicity. But that's about
Hmm.
it.
Hmm.
Chaotic
Hmm.
sets can have different topologies depending on the number of positive Lyapunov exponents and other properties.
Hmm.
But there are not so many different, terribly many different possibilities. Yeah? So
Hmm. Hmm.
that might be close to it. Yeah.
Okay, so that's a very interesting point. I want to push that a little further. So, I don't have, you know, I'm not trained in dynamical systems, so I don't know if this is this makes any sense, but I wanna connect this to what you would get from, for example, vision. So it turns out that things like edges are a good basis to compose. You can compose any real natural image from a basis of those edges, which are also known as gabors. And then you would see this in the primary visual cortex. So that's kind of a compositional basis to compose any shape that you would see in anywhere. Is there something similar to that where we can think of that as maybe even yeah, in dynamical systems theory, is this mathematically identifiable? Can you come up with a basis that actually is a good basis for composing them and to get to new dynamics? Is that viable?
Mm, yeah, that's a very good question. I'm not 100% sure, to be honest. As I
Hmm.
said,
Hmm.
there's a sort of a finite set of potential topological motives,
Hmm.
um, or at least a countable set. But So let's put it this way. If you we in the original dynamics paper, we also studied a bit what the different experts would focus on. Yeah? And they
Hmm.
focus
Hmm.
on different, they don't focus like it's not like one expert learns fixed points and the other one learns
Hmm.
chaotic
Hmm.
trajectories or something like this. But they focus on different sort of temporal segments. Yeah?
Hmm. Hmm.
So different trajectory bits with different geometries. So you might
Hmm.
want to think of that there are basic motives, um, yeah, from which you can um, compose it in a similar way to the visual system. Yeah? Because I mean, there's also
Hmm.
an
Hmm.
infinite
Hmm.
number of possibilities, of course, also in vision. Yeah,
Hmm.
so how you want to arrange all
Hmm.
the luminances and all these.
Hmm.
It's a continuous set, but you can capture a lot with just
Hmm.
a finite set of
Hmm.
Gabor functions or something similar.
Hmm. Hmm.
Yeah, and the similar thing might be going on here. Yeah, that's a possibility.
Hmm. Thanks for the clarification. I do have one more question. It's more of like trying to interpret these almost linear RNNs. And I don't know if this question makes sense, so let me just try to motivate it. But okay, maybe before I ask that question, there's somebody who raised their hand. Do you want to go first, or Axel?
Yeah, sure. I'd be happy to go. Thanks.
Hmm.
Thanks
Yeah.
for the talk. Really interesting. So I come more from an experimental background. So we work with EFIS data, and so you mentioned that comparing dynamical systems reconstruction with like tools like Zebra, you get more of a reconstruction model. Could you kind of unpack what one can then do with that and how one can go back to behavior? Because from a more experimental point of view, we're often just interested, okay, we have spike counts and we want to know how that relates to behavior. And there maybe you could unpack this a bit more. Thanks.
Yeah, so the what I meant by that is that on top of this latent space or representation, you get a reconstruction model. Yeah, so you get a recurrent neural network. Sorry for flipping through the slides here. You get a recurrent neural network that is a that you can use as a surrogate. Yeah? So that you can examine like a computational model. You have a computational model on top of this representation here. You have a computational model of the underlying system that generates. So this is simulated activity from this computational model. Yeah? So it's generated activity. And then you can analyze this computational model just like you do analyze other computation models in computational neuroscience. Yeah, so you can look for the let's say for the attractors in this model, and maybe be able to come up for an account or with an account of your experimental data in terms of these different attractor objects in the data. You might discover, for instance, manifold attractors in this reconstructed model.
I'm still a bit confused. So I suppose if you have the model, it's not. I'm less familiar with dynamical systems theory, but how would you probe the model? What like would you also then like I don't know use dimensionality reduction techniques on like the activation function of the RNN, or like what does probing the model mean practically?
Yeah, so for us, probing the model means we're really mathematically analyzing it. Yeah, so we keep them piecewise linear because then we have very efficient algorithms to really extract attractors or extract basins of attraction, yeah, or extract the boundaries between basins of attraction. So we can reveal this dynamical landscape, yeah. And from our theoretical neuroscience point of view, this dynamic landscape is what implements the computation. And so that is in fact what we want to know. But from a more experimental point of view, you might also want to. The relevant question might be now, okay, so how can you test this further? Yeah, and that for that you can also use the model. Yeah, you can simulate, for instance, perturbations into the model. So many of the things I haven't shown here, but you, for instance, can configure the decoder models of this underlying recurrent neural network in such a way that you can discriminate different cell populations in your recurrent neural network. And then you can, for instance, simulate optogenetic experiments in your recurrent neural network and can take that as a prediction for your experimental setup.
Okay, that seems very interesting. So I could, I don't know, turn off a third of the population and then look how the latent reconstruction, similar to the one on the plot you're showing, looks differently. Okay, that seems very
Exactly.
helpful. I think I'll try to do that. Awesome, thanks.
Okay, sure.
I do have one more question that I want to ask before we go. So I want to try to interpret this the inferred almost linear RNNs. Another way to get to the recurrent circuit is start from a loss function. Just say that I posit that this circuit is trying to minimize this loss function, and then the gradients of that loss give you the dynamics. And I wonder if you can do this the other way around. You start from the inferred ALRNN, and then from that, do one more step and infer what kind of like a Lyapunov function or something they're trying to minimize.
Yes, I think I know what you mean.
Mm-hmm.
Because you have given this, so for a recurrent neural network, you can explicitly compute the Lyapunov spectrum, yeah, because you do have the Jacobians, yeah, so you don't need to infer it empirically, yeah, like for empirical data. So because you can compute this product series of Jacobians, and so you could indeed try, and partly people have done so, to use this as a regularization criterion in your loss function. Yeah? So to train the model for a certain Lyapunov spectrum.
Is that useful in terms of giving you some more intuition, that you can interpret what this dynamical time series is actually really trying to accomplish, or that's not really the way to think about this?
I think the tricky point with this is, let me first say how people have used that. So that basically, there was work by Henry Abravanel's group in San Diego. They have done this, and but they used it more to force a reservoir computer to get the long-term properties right. Yeah? So they empirically inferred Lyapunov exponents from data, and then they use it as a regularization constraint. Now, of course, in reality, you often don't. You need to infer this from data itself, yeah? And your empirical inference is not so easy. Yeah? So I would say this wouldn't help you too much for many systems. Yeah, in many complex systems like the brain, you would want to go the other way around. Once you have a model, then you can use it and compute the Lyapunov spectrum from that.
Yeah, that makes more sense. Joshua, go ahead. Is the speaker familiar with the work of William Galpin? He designed a model for nonlinear dynamics pre-trained on chaotic ODEs generated with ES. Could be useful.
Yeah, so we know this work, and I think we actually compared to it. Let me see. It should be somewhere in the dynamics table. So I think this model, this Panda model, I actually discussed it with William quite a bit. It has a different intention. Yeah, so it was not conceived. Okay, is it somewhere in here? Yeah, here it is. It was not conceived as a dynamic systems reconstruction model. It was conceived as a model which was trained on dynamic systems, but for the purpose of short-term forecasts. And that it does quite well. So it outperforms many of the other time series foundation models. But it's not in the sense we use the term a reconstruction model, I would say. And I think William would agree with it.
Okay, perfect. If there are no more questions, let's thank the speaker again. And thank you so much for this amazing talk, as well as being flexible with the start time. I'm gonna stop recording now.